In this lesson, we are going to discuss the refraction of light. At the end of this video lesson, you should be able to state the law of refraction and solve problems using the law of refraction. In this situation, a light source emits a ray of green light into a prism. As the green light enters the material, it appears to be broken or bent. This phenomenon tells us that the light is refracted. Refraction happens when the direction of light changes as it passes from one medium to another medium of different optical density. Optical density is the measure of absorbance of light. The optical density of a substance has something to do with the speed of light as it enters the substance. Light travels slowly in an optically dense substance. A substance is said to be optically denser if it has a higher index of refraction. The index of refraction is the ratio of the speed of light in a vacuum to the speed of light in another substance or material. It is defined by N is equal to C over V. N is the index of refraction, C is the speed of light in a vacuum equating to 3 × 10⁸ meters per second, and V is the speed of light in a substance. The index of refraction tells us how much slower will the light travel in a certain substance as compared to when it travels in a vacuum. Given the formula for the index of refraction, we can solve for the velocity of light in a certain substance using V is equal to the speed of light in a vacuum over the index of refraction of the substance. The index of refraction is generally unique to each substance. Let us compare the index of refraction of the following substances. Here we have air, ice, water, and glass. Air, which has an index of refraction of 1, would allow light to travel at 3 × 10⁸ meters per second, the same with the speed of light in a vacuum. To get the speed of light in ice at 0 degrees Celsius, we divide 3 × 10⁸ meters per second by the index of refraction of ice of 1.31 to get 2.29 × 10⁸ meters per second. In water, the speed of light in a vacuum is divided by 1.33 to get 2.26 × 10⁸ meters per second. Lastly, for glass, the speed of light in a vacuum is divided by 1.52 to get 1.97 × 10⁸ meters per second. These substances are listed in increasing index of refraction. This corresponds to decreasing speeds of light. This shows that a substance is optically denser than another if its index of refraction is greater. And the higher the index of refraction, the slower the light will travel in the substance. Aside from the speed of light, the index of refraction also tells us how the position of an object seems to change as viewed from the outside of the substance. A lot of phenomena show this result of refraction. For example, a pencil or a straw appears to be bent in a glass of water. Even fishing using an arrow uses refraction. One should not aim directly at the fish where it appears to be because the fish is not there. This phenomena can be described by the ratio of the object's real depth to its apparent depth. In swimming pools, the depth may seem to be shallow, but it is possible that the pool is actually deeper. The object in this case, which is the pool's tiled floor, seemed to be shallower because of refraction. To look closer on how this is possible, let us look at the certain word problem. While sitting on the ledge of a pool, Jerome's feet appear to be submerged at a 0.4 meter depth. If the refractive index of the pool water is 1.33, what is the real depth of Jerome's feet? To solve for this problem, we are going to use the previous formula. To completely isolate real depth, we multiply the apparent depth to both sides of the equation. Substituting the values, we have 1.33 multiplied to 0.4 meters. Thus, the real depth of Jerome's feet is at 0.53 meters. This shows how our feet seem to shorten when we submerge it in the pool water. In this case, Jerome's feet seem to shorten by 0.13 meters. After discussing how objects are affected by refraction, let us now discuss how refraction really happens in the context of geometric optics. These two divisions show the two layers that will be the passageway of light. The upper medium, in this case, medium 1, has a refractive index of n sub 1. Light will be incident to the refractive boundary. This ray is what we call the incident ray. From the boundary, an imaginary perpendicular line will be drawn as a basis of the angle measurements. The normal line will create an angle together with the incident ray. This is what we call the incident angle or theta sub I. Since this is refraction, the light will continue to pass through the second medium with a refractive index of n sub 2. The ray will appear to be bent. This is called the refracted ray. The deviated angle formed by the refracted ray and the normal line is called the refractive angle or theta sub r. The incident ray, refracted ray, and the normal line all lie on one plane as stated by Snell's law. This also states that the product of the index of refraction of the first medium and the sine of the incident angle is equal to the product of the index of refraction of the second medium and the sine of the refracted angle. In determining the angle, starts with dividing both sides of the equation by n sub 2. Now, we can see that we haven't completely isolated theta sub r. We cannot divide both sides by sine because sine is not multiplied to theta sub r. It is rather a trigonometric function of the angle. Thus, we need to get the inverse sine of both sides of the equation. This is denoted as the arc sine. By getting the inverse sine of both sides of the equation, we can cancel the sine function of theta r. Thus, we are left with the inverse sine of n sub 1 times sine theta sub I all over n sub 2. Let us look at two different setups to practice Snell's law. In these two setups, glass, which has an index of refraction of 1.523, stays on top of quartz and sapphire with indices of refraction of 1.46 and 1.77 respectively. To compare how the angle of refraction is affected by the index of refraction, we are going to use the same incident angle. Here, the light ray will hit the refractive boundary at 45 degrees from the normal for both setups. Using the previous derived formula, let us solve for the angle of refraction on the glass to quartz layers. We have the inverse sine of the index of refraction of glass, which is 1.523, multiplied to the sine of the angle of refraction, which is 45, all over the index of refraction of quartz, which is 1.46. This expression should result in an angle of refraction in the quartz layer of 47.53 degrees. On the other hand, we have the inverse sine of the index of refraction of glass, which is 1.523, multiplied to the sine of the angle of refraction, which is 45, all over the index of refraction of sapphire, which is 1.77. This expression should result in an angle of refraction in the quartz layer of 37.48 degrees. As we can see here, in the first setup, light passes from a denser material to a less dense material. The result is that the refracted ray deviated away from the normal line. In the second setup, the light passes from a less dense material to a more dense material. The result is that the refracted ray deviated towards the normal line. To connect the speed of light in a certain medium to the law of refraction, let us answer this problem. A ray of light travels from zirconium, which has an index of refraction of 2.2, into a diamond at an angle of incidence of 75 degrees. It is deviated by 13 degrees when it refracted into the diamond. What is the speed of light in the diamond? As stated in the problem, light first travels in zirconium with a refractive index of 2.2. It creates an angle of 75 degrees from the normal. Next, it will refract to the second medium, which is diamond, with a deviation of 13 degrees from the original angle. That means that the angle of refraction is closer to the normal line by 13 degrees as compared to the angle of incidence. Thus, we subtract 13 from 75. We now have an angle of refraction of 62 degrees. We are asked to solve for the speed of light in diamond, but we have learned that we need an index of refraction to solve for it. Thus, we also need to solve for n. We are going to use Snell's law to solve for n since we have n sub 1, theta sub I, and theta sub r in the given. To completely isolate n sub 2 or the index of refraction in diamond, we are going to divide both sides of the equation by sine theta sub r. Take note that we did not do inverse sine because we are not removing the sine function of the refracted angle. Substituting the values, we are going to have m sub 2 is equal to 2.2 multiplied to sine 75, all are divided by sine 62. Computing this will give us 2.41 for the index of refraction in the diamond layer. Now, we can solve for the speed of light in diamond by using n is equal to c over v. To get v, we have c over n. Plugging in the values, we have 3 times 10 raised to 8 meters per second over 2.41. Computing this, the speed of light in diamond is 1.24 times 10 raised to 8 meters per second. And this is how we solve word problems on refraction of light. To conclude this lesson, let us review the following key points. Refraction is the change in the direction of light when it passes from one medium to another of different optical density. The index of refraction of a substance, denoted by n, is the ratio of the speed of light in a vacuum to the speed of light in the substance. The index of refraction may also be obtained from the ratio of the real depth of the object and its apparent depth. The law of refraction states that the incident ray, refracted ray, and the normal lie in one plane. And lastly, the law of refraction also states that when ray passes obliquely from a less dense to a denser medium, it is refracted toward the normal. And that ends our discussion on the refraction of light.